alkenes can be hydrogenated by the addition of H2 across the double bond. This requires a metal catalyst, and which consists of either platinum, palladium, nickel, or ruthenium. Typically, palladium or nickel are used. And this is syn addition. And SYN, syn addition, means that the hydrogen atoms will add to the same side of the double bond. Now let's take a closer look at this. Step 1, the hydrogen adsorbs onto the face of the metal. And then the alkene approaches, kind of sits right down on there, and then the hydrogen atoms are added to the same side of the double bond as seen right here. We can oxidize a double bond using permanganate. This is typically a chemical test. The product is a glycol, which is an 1,2-diol, right? So it's a alcohol, 2 alcohol groups on the molecule, and manganese dioxide, which is a brown, it looks like a melted brown crayon, actually. So here's what happens. It's a complex reaction mechanism, and it goes through a 5-membered cyclic ester intermediate, which you will be introduced to later on in the course. The important point here is the result of the reaction. You're not responsible for the mechanism of this reaction at this point. But please, let's start with an alkene, and here's potassium permanganate, which is very nice, dark, rich purple color. In water, the permanganate will add and create a glycol, which is a molecule with 2 OHs. MnO2, again, this is a brown precipitate, and KOH. So the acidity or the pH of this reaction will be rather basic. Another important oxidation reaction is called ozonolysis, and this actually cleaves or breaks both the bonds in an alkene. You can see this first step. The dashed red line indicates where the molecule will break. We're reacting this with ozone and then zinc under acidic conditions. When you see an H+, it indicates acidic conditions. And this will actually form 2 species, each containing a double bond, oxygen. In this case, when you have 2 R groups, this indicates a molecule called a ketone. Where you have an R group and an H next to the double bond, this indicates an aldehyde. Here's the scheme for ozonolysis. So the pi electrons will act as a nucleophile attacking the ozone at the electrophilic terminal. And we form this 5-membered ring with the 3 oxygens. So the blue arrows here indicate movement of electrons. So they will break apart the alkene in the following manner. They'll form a species with a double bond, oxygen, and another species with 2 oxygens. That will then, again, attack the double bond oxygen species in this manner, forming a species called an ozonide. Notice the oxygens, we still have a 5-membered ring, but the oxygens have kind of moved around or traded places. Now that ozonide will react with water and fall apart in the following manner. The first product is going to be this species here, and the second product will form a peroxide and this species. Let's back up a bit and look at the general scheme, because this is important. An alkene in the presence of ozone will form this molozonide species. Notice the formation, or the formation, I guess, of the oxygens. That will what's called rearrange. So the oxygens will move around through that molecule, still a 5-membered ring, but now we have 2 oxygens and then 1 oxygen up on top. When that now is subjected to zinc metal under acidic conditions, they will be cleaved or broken apart to form our 2 species. So alkenes can also undergo radical addition reactions. And this is capitalized on or used in the formation of polymers, synthetic polymers. And let's take a look at this. So we're going to need an organic peroxide. That's a species with an oxygen bonded to an oxygen. Typically it's T-butyl peroxide or benzoyl peroxide. And upon heating that, we'll break that molecule apart. Breaking the oxygen-oxygen bond will form two radicals, two oxygen radicals. Those oxygen radicals can now add to that double bond of the alkene, to the pi electrons, forming a carbon-centered free radical. So the alkene breaks apart, forms a bond with our catalyst, and then the other electron goes over to this carbon here to form our radical, which is right here. So chain growth occurs, and that is the actual process of polymerization. So we've got our species with our carbon radical. That's going to then interact or react with another molecule of ethene. This will break homolytically, meaning evenly, and each electron will go to a carbon. That will add to this, creating a radical down the chain. See, we've added the ethene molecule. And this will continue and continue and continue until a termination step occurs, where two carbon radicals will react with each other. During the chain growth, a branch point can be introduced if the chain wraps back on itself. So what that means is that you will not have clean linear chains, but you may have branched chains. Just as you can have branched alkanes with a smaller molecule, you can have branched polymers. So let's look at addition to a conjugated system. And I'd like to remind you what a conjugated alkene is. It contains two or more double bonds, but the important point is they're spaced apart by one single bond. You have a double bond, a single bond, and a double bond. Now, in this example, notice we've got two hydrogens down here. This is a secondary carbon. This is a secondary carbon, but this is a tertiary carbon because we've got two methyl groups on it. So let's go through this mechanism and understand what's going on. The electrophile will add a proton, and according to Markovnikov's rule, we're going to form a secondary carbocation, which is more stable than a primary. We still have this other double bond here. Now, it can do two things. We can draw a resonance structure, which will move the double bond over here and create a carbocation here, shown right here. Now, that's interesting because that's a tertiary carbocation, right? That's more stable than a secondary. If that occurs, we'll form what's called the 1,4 addition product. So we can count. The hydrogen went on here. That's 1, 2, 3, 4. That's the 1,4 addition product. Now, if the carbocation stays in this position as a secondary carbocation, the bromide will attach right here. That's a 1,2 addition. Okay? 1, 2. That's a 1,2 addition. So in this case, there's going to be much more 1,4 because it reacts through a tertiary carbocation, which is more stable than a secondary carbocation. While we're on the topic of conjugated alkenes, there's another type of reaction that's very important in organic chemistry, and that's called a Diels-Alder reaction. This requires a conjugated alkene, and it's described as a cycloaddition reaction. So let's look at this reaction in a little bit more detail. First, here's 1,3-butadiene. Butadiene. Two double bonds in the molecule. They're separated by one single bond. That's going to react with another species, another double bond species. In this case, for simplicity, it's just ethylene. And remember, the arrows here show the movement of electrons. When they're double-headed, they show the movement of electron pairs. In the radical mechanisms, they're single-headed or fish hooks. They show the movement of a single electron. So here we're moving electron pairs. So I like to explain this in the following manner to new students. Picture this as a door hinge. This is fixed right here. This part swings out in this manner, creates a bond over here. Here's another hinge. It's fixed. It swings down and creates a bond here. The final time, this is hinged and it swings over to create a double bond here. And all of this electron movement occurs simultaneously. It is what's called a concerted reaction. So let's look at our product, which is cyclohexane. We've created a new pi bond, right? Here's our double bond. Here's our new sigma bond. And here's our other sigma bond. Now, for simplicity, we just showed butadiene and ethylene. In real-world synthetic chemistry, we'd actually have other groups on there to create a more interesting or usable product. So we can look at things that are dienes and things that are dienophiles. So a diene, obviously, is a structure or a molecule that contains two double bonds. It can be butadiene, as we've seen. It can be a cyclohexane or cyclohexyl ring with a conjugated system, or even a cyclopentyl ring with a conjugated system. The dienophile is a species which seeks out a diene. There's only one double bond here. In our initial example, this was only ethylene. So now we're using a molecule that contains a ketone species. In this case, we have a cyano group. Here we have a diester. These groups are ester groups about our diene. This is maleic anhydride. This is very commonly used in undergraduate laboratories in the Diels-Alder experiment. And there are many, many others to choose from. So let's look at a more complex example. We'll start with butadiene and react it with this diester. Here's our double bond. Here's our product. Now the stereochemistry is very important in this reaction, and that's what this slide explains. Notice both of these ester groups are coming out at you, right? The solid wedges mean that that group is coming out of the paper or out of the screen at you when they are cis. Here, same diene, but now we have a trans configuration, right? Trans configuration, because that cannot rotate about that double bond. And in this case, we form a cis product where the lower ester group is going into the paper or into the screen, and the top one is coming out at us. So the stereochemistry of the reactants is preserved. So there's no breaking of that double bond for rotation. Rotation cannot occur. So a trans dienophile gives a trans substituent in the product.